Hello, my name is Wei-Chen Lin, also known as Tom Lin. I'm currently a PhD student at the University of Bristol's HPC group. My focus is on various portability properties of HPC languages and frameworks. I started using SYCL back in 2019 when I started porting HPC mini apps from the original implementation to SYCL. I remember during that time we only had one production-ready SYCL implementation, which is Compute CPP, I think. So yeah, we've come a long way. Since then, we got a few more mature SYCL implementations, such as Intel's DPCPP and HipSYCL. Shameless plug here. I actually wrote a paper for iWalkle earlier this year that tracks the performance improvements for SYCL compilers over time. I'll put a link to the PDF at the end of the talk so you can read the conclusion there as well. So looking to the next 12 months, I'll probably be porting some of the older SYCL applications in my group to use the SYCL 2020 spec. So hopefully more compilers will pick up the changes over there. Okay, so in this talk, I'll present a interactive real-time 3D fluid simulation mini app. So this mini app is implemented using the SPH method, and we're going to reconstruct the surface of the SPH fluid using marching cubes and Metaballs. The simulation covers both traditional HPC workloads with a focus on real-time visualization. I'll first show the mini app implemented in OpenCL. Then we'll progressively present changes needed to port the mini app to SYCL. And finally, I'll show a SYCL 2020 version that is able to run on most SYCL implementations. Okay, so SPH stands for Smoothed-Particle Hydrodynamics. As the name suggests, this is a computational fluid simulation technique. This method is conceptually quite simple, sort of like a traditional n-body simulation. The main idea here involves finding the neighboring particles within a given radius and apply some sort of convolution kernel. We do this for all the particles for every step of the simulation. SPH has a few interesting properties. First, it is a mesh-free method so that we can track the position and the velocity of each individual particles. This makes in-plane collision and diffusion relatively easy. Second, as this is a discrete method, parallelization becomes straightforward. We only need an array that holds all the particles and a step function to compute the next position of each particles. Before I dive into the implementation details, let's take a look at the end result for some motivation here. This is a screen capture running on my machine. So it's a 12-core Ryzen 3900X machine running on the latest HipSYCL release. Runs about 30 frames per second here. Notice the diffusion on the two different color particles. We can turn on the surface generation as well. This is going to reduce the frame rate by quite a bit. We can also play around with the simulation parameters live using the controls on the top right. And it looks like I broke the simulation a bit. Okay, let's move on. This implementation is derived from the excellent position-based fluid paper by Mellis Macklin and others. I encourage everyone to give it a read for more details on the maths. As the focus of this talk is on the productivity side of SYCL, I'll quickly summarize the theory of operation here. First, given a particle with a known velocity, we can predict the future position using that velocity. We call this new position p star. Then, we enforce a constant density constraint for the particle. The idea here is that we want to keep the density of our particles equal everywhere, just like in real fluids. For example, water is incompressible here, so it makes sense. This step involves solving for a correction term lambda based on the neighbors of the particles. Finally, we update the position of the particles to p star along with the lambda term. To create a 3D surface from the fluid point cloud that we just created, we'll be using the tried and tested marching cubes method. The main challenges are as follows. We need to implement a fast nearest neighbor search that runs well on both CPUs and GPUs. We also need to implement marching cubes on both CPUs and GPUs as well. To implement all these in a productive manner, we require the underlying framework or language to be expressive. I'll be implementing the mini app in 3 frameworks: OpenCL, OpenMP, and finally SYCL and SYCL 2020. We then compare these implementations to show how SYCL improves on the productivity end. Before I start discussing each of the implementations, let's go through the theory behind a fast nearest neighbor search and marching cubes. To implement a fast nearest neighbor search that works well on both CPUs and GPUs, we'll be using a technique called spatial hashing on Morton codes, also known as a space-filling Z-curve. Briefly, Z-curve gives you locality-preserving indexing from simple linear indices. The idea is that with a 1D array of elements, we can reorder it to fill in an arbitrary hypercube. To put simply, for 2D, this means you get a square, so a quadtree, and for 3D, you get a cube, so an octree. With an octree, you can efficiently get the 27 adjacent cells in 3D space by simply offsetting each component of our vector coordinates by 1. So this all sounds very abstract. Let's see how it's done in practice. So let's say we want to find out the nearest neighbor at some point A in 3D space. On the left, we have the naive version that goes through all the particles and find the nearest ones within some given radius. In SPH, we need to compute the nearest neighbor for each particle. So if we do this, the complexity here becomes n squared, where n is the particle count. So this doesn't scale very well. With Z-curves, we can do the search in near constant time. First, let's construct the hash table. On line 1, on the top right code block, we first compute a Z-curve for all the particles. We divide the position by some cell units so that each Z-curve index contains multiple particles. Then, we sort the particles by Z-curve index on line 7. At this step, we can already find each particle's neighboring particles by going backwards and forwards in the sorted array. Line 9 and 10 shows what the array might look like. For example, you see that 4 particles have a Z-index of 1, and are clumped together thanks to the sort. Recall that we divide 3D coordinate space with the cell units. That means that we can get all the particles that share the same approximate position by reversing the Z-index lookup. We create a prefix sum hash table that's shown on line 11 to 14. For querying, simply compute the Z-curve index of point A along with the offsets of the 27 adjacent points in space. As shown on line 7, for each of the 27 Z-curve indices, we use prefix sum hash table to work out what the index of the particle is in the sorted particle array. Compared to the naive version, this means it takes near constant time for any arbitrary large particle count. This is also GPU friendly as we only need to pass an extra hash table, which is just an array of prefix sum integers. Okay, so to create a 3D surface from the fluid point cloud, we'll be using the marching cubes method. At a very high level, we'll be creating an implicit surface using Metaballs. The idea is that particles close together gets merged into a geometrically smooth manner, like shown in the figure, with the red and blue particles. The implicit equation for computing the 3D scalar field is shown in the middle. Here, the vector v is our place vector, and n is the particles neighboring the vector v. For our case, we create a scalar field by sampling the point cloud with a constant offset. The point at which we take a sample is the place vector, v. Once the scalar field has been created, we use the marching cubes algorithm to create a surface by traversing our scalar field as shown in the bottom left figure. Marching cubes work by generating triangles in known configurations without traversing the field. The original algorithm requires dynamic memory allocation because the total amount of triangles generated isn't known until the algorithm completes. So for this to work on the GPU, we need to execute marching cubes twice. The first iteration is a reduction that only computes the amount of triangles required. Once we are certain of the memory requirements, we can complete the algorithm normally in the second iteration where we save the triangles to the allocated memory. So that concludes the SPH theory and surface reconstruction part. Now that we have all the background, let's discuss the actual mini-app. So I create 2 drivers, one with a live visualization that I saw a few slides ago, I use the polyscope library to render the graphics and controls. The second driver is a benchmark driver. This driver only exposes a command line interface, so it does not require any of the OpenGL or GLFW bindings that polyscope requires. We want the interface of the solver to be simple. Here's the code snippet that shows the simulation in a loop with some given initial particles and some parameters. So this is a pretty typical simulation loop kind of thing here. Crucially, we want the solver to be parametric on a few things. First, the particle should support tagging, so that we can track the particles after each step. For example, the snippet here is using size t. Then, we also want to be generic on the number type. That way, we can select between performance and precision. Finally, we expose the underlying vector type of the interface. This way, we avoid extra copies to a common vector type. The following snippet shows the concrete interface and models that we'll be using. Each implementation will extend from the solver class on line 24. To implement SPH, we need 4 kernels. First, the diffuse kernel computes any color diffusion between the neighboring particles. Then, the lambda and delta kernel is run on a loop to compute the pressure term lambda. Anything above 3 iterations of the lambda and delta kernel usually gives good results. Finally, we update the position in the finalized kernel. For marching cubes, we'll need 3 kernels. First, we create the Metaballs scalar field for the marching cube algorithm using the lattice kernel. Then, we proceed to compute the space requirements with a partial marching cubes kernel called tsum. Finally, we run marching cubes for real in the evaluate kernel. Here, I'll go through a traditional OpenCL implementation of the miniapp and highlight some of the pain points. First, we compute the z-curve hash table on the CPU. We also sort the particles at this step. Then, we copy the particles to a standalone structure that holds our particles. We need to do this because we can't reuse our templated C++ particles in OpenCL's C dialect. Due to time constraints, I only implemented a specialized version where the particles tag is fixed to the unsigned integer type, and we're using floats for the vectors. In theory, we can parameterize the OpenCL version with some clever macros, but that would just be implementing C++ in C with macros, so not a very productive thing, so I decided to not do that. On the productivity side, writing the kernel in OpenCL's C dialect also highlighted some of the biggest weakness of OpenCL. Our fast nearest neighbor approach is best implemented as a separate function, so we'll be using it in almost all of the 7 kernels. With OpenCL, the best we can do here is a horrible macro here to reuse the nearest neighbor logic, as function pointers are not allowed, so it's kind of annoying here. For implementing a small-scale application like this, OpenCL's separate source model makes experimenting with algorithmic changes a high overhead operation. Despite using the C++-based OpenCL header, we will still have to keep the kernel signatures in SYCL manually, which is very error-prone. As OpenCL is a C99 dialect, code sharing between the kernel and driver can only be done in headers in the limited way. For example, C++ constructs are also not allowed, as it prevents the kernel from compiling. In our case, we simply can't template the kernels to accept arbitrary numeric types. We also can't use some C features such as function pointers. In addition, existing debugging tools such as address sanitizers don't work well under OpenCL's execution model, although there are OpenCL-specific debugging tools that fill the gap, such as OCL grind. Now let's move on to the CPU-only OpenMP implementation. We're back to C++, so we can take full advantage of the language features here. First, we can use the particle models we have defined as part of our solver API. So we do have to create new models for that. This saves us from having to copy to and from a special model for the framework we're using. So that saves a lot of maintenance work here. Next, the macro we had to write in OpenCL for the nearest neighbor search can now be a proper templated function as shown here. So this all gets inline properly. There's no extra lambda overheads, hopefully. Previously, in OpenCL, we have to define the kernel signature in 2 files. As shown here, we have to manually keep the signatures for the host and device synchronized. This process is actually quite error-prone, and it's not exactly easy to debug issues if we accidentally pass the wrong thing, or if we pass in the parameters in the wrong order, say. In OpenMP, this is a non-issue as we write the kernel inline in the same file. The kernels will simply be a for loop that captures whatever variables we have in scope at the time. For OpenMP, compilers supported debugging tools such as address centers that work very well here. We also get to make full use of C++ language features here. Finally, we avoid having to maintain multiple variants across 2 languages like in OpenCL. As expected, OpenMP served the gold standard of productiveness for use on CPUs. Now let's see if SYCL can match this. Writing from OpenMP to SYCL is relatively straightforward. We replace all the for loops in OpenMP with a queue submission while keeping the loop body. We can almost keep the loop body exactly the same as the OpenMP version as shown here. The only extra thing we have to worry about is the buffer management. For the parallel reduction kernel, psum, we implement a variant of the tree reduction just like the OpenCL version. The SYCL 1.2 spec doesn't really include a built-in reduction feature like OpenMP does, so we have to roll our own here. Now, let's see if we can do even better. The new SYCL 2020 standard allows us to remove quite a large amount of boilerplates here. By using the new Unified Shared Memory feature, or USM, we can avoid having to write explicit buffer capture code. SYCL 2020 also provided a simplified parallel for syntax, so we no longer have to nest everything in 2 layers of lambda expression. In the end, I was able to achieve up to 200 lines of code reduction from SYCL 1.2. Looking at the structure, the SYCL 2020 version looked very similar to the OpenMP version. It had a sort of similar line count there. The only part that was still unsatisfying is the psum reduction. SYCL 2020 introduced a new reduction function which is similar to parallel for. Unfortunately, not all of the current SYCL implementations support this feature, and for the ones that do, some of them have slightly different interfaces, so they aren't really compatible yet. Yeah. To summarize, we were able to get close to OpenMP levels of productivity with the SYCL 2020 version. We were able to retain the same level of debugging friendliness in OpenMP by running our SYCL implementation on the SYCL host device. In this mode, Address Sanitizer was able to warn me on common errors like accessing out-of-bound elements, and it was able to do that with the same level of precision as it did with the OpenMP version. So that's really good for debugging. In certain cases, the sanitizer still worked when we use an actual device. So for example, in HipSYCL, which delegates to OpenMP, Address Sanitizer worked perfectly there. And same thing with CPP on the TPP backend as well. As developer productivity is one of the core factors in influencing the success of a software project, I think SYCL represents a huge improvement on the productivity front over the traditional OpenCL model. Finally, you can find the source code of this miniapp in our group's repository. This code is open source, so feel free to play around with it. That's it. Thank you very much.